ado, I would like to introduce our very first speaker today, joining us all the way from Belgium. Peter is a lead machine learning engineer at Aspect Analytics. Aspect Analytics is a bioinformatics startup working on a large-scale analysis of mass spectrometry imaging data, MSI data. At Aspect Analytics, the team intend to use Dask, a distributed computation library for Python, to deal with MSI data stored as large tensors. In this talk, Peter explores using Alluxio and Alluxio FUSE as a data consolidation and caching layer for some of the bioinformatic workflow at Aspect Analytics. So let's hear from Peter at Aspect Analytics on Alluxio FUSE as a data access layer for Dask. Peter, take it away.
Alluxio Day presentation, good slides, show this one now. All right, good morning or good evening, everyone. I hope you can all hear me. So I'm here to present how Aspect Analytics uses Alluxio together with Dask to build a bioinformatics analysis pipeline for mass spectrometry imaging. Let me see, I can go through my slides. Yes, perfect. All right, first, who am I? I'm Peter. I'm a machine learning engineering lead at Aspect Analytics. And during the last half year or so, I've been looking into using both Alluxio and Dask to facilitate our Python-based analyses pipelines. And so in this presentation, I will first start out with quickly introducing Aspect Analytics, to explain our use case. I will then move on to Dask and Alluxio, and how we can use Alluxio as a data access layer for Dask via the FUSE POSIX API. So Aspect Analytics, who are we as a company and what do we do? So Aspect Analytics is a bioinformatics spin-off from the University of Leuven in Belgium. We are a software company dedicated to mass spectrometry imaging bioinformatics. Mass spectrometry imaging is a relatively new molecular imaging technology that is increasingly being adopted in biomedical R&D and drug discovery. These mass spectrometry imaging techniques are known to generate large amounts of data. A single image can already be in the order of hundreds of gigabytes, with data sets of multiple images running into the order of terabytes. And to deal with this large amount of data coming from these imaging techniques, and to enable various downstream analyses, we're building a platform to support our clients' workflow and analyses based on their data. Now, I hear you thinking, what exactly is this mass spectrometry imaging? And to give you some context, I will briefly explain this in two parts. And so first, the first side of it, there is like the mass spectrometry side of things. And mass spectrometry is a technique that, given a chemical sample, allows you to measure the abundance of molecules by their weight. And the output, as illustrated here in this figure, is a histogram of molecular weights, where the x-axis here can be loosely interpreted as bins of molecular weight, while the y-axis is related to the molecular abundance given in these bins. And so this histogram is also what is known as a mass spectrum. And each peak shown here could be interpreted loosely as a different kind of molecule, neglecting isotope effects. And so now about the imaging part of mass spectrometry imaging. So when given a slice of tissue, as is illustrated here in this figure, we can measure the mass spectrum of different pieces of this tissue. In fact, we can actually divide this tissue into a grid of so-called pixels, just like an image is divided into pixels. And now when we measure the mass spectrum at each pixel in the grid, as is shown here, we get something that looks like an image. And the main difference is that instead of having only 3 channels, like the typical red, green, and blue channels in an image, we can now have up to 1 million channels, where each channel is a bin from our mass histogram. And these so-called images are also known as hyperspectral images. And so the resulting data that we get looks a bit like a cube or a 3D tensor, where similar to a regular image, you have like 2 spatial dimensions, the x and the y here, and then an extra third dimension along the molecular mass bins. And a single data cube, which is the output of scanning one piece of tissue, is what we call a mass spectral image. Another way of viewing these mass spectral images is as a stack of so-called ion images. And this is what illustrated on the left here. The data cube can be sliced into these different ion images, and each ion image corresponds to a specific mass bin in the mass spectral dimension. And this is a bit illustrated here on the right, where like we have like one single pixel value, and then we have different mass bins, where if we take the full slice along the image, we get like these visualizations here. And so these ion images, these visualizations here, they're a bit similar to single channel or like grayscale images, as you know and familiar with. Note that in this image, they're actually not grayscale, since we typically use a different color map to visualize them. So to summarize, a mass spectral image is like a data cube and can be seen as a stack of images. And each image corresponds to the localization of type of molecule in the scanned tissue. And a typical mass spectral image like this can have like 500 to 1000 pixels in each spatial dimension and 100,000 to even like 1 million mass bins, which quickly leads to around 100 gigabytes or even 1 terabyte per single mass spectral image. You can imagine that data sets of multiple of these images grow quite large very quickly. And so given these mass spectrometry images, we at Aspect Analytics, we provide various unsupervised machine learning methods that capture the important features of the data. An example, for example, we have matrix factorization-based methods, clustering-based methods, manifold learning methods, and extracting these features and patterns helps our clients with biomarker discovery, which can then lead to new diagnostic tests. The data also allows us to spatially localize and visualize certain biomolecules. We and our clients can use this to analyze different regions of the image tissue. For example, in the image shown here, we have blue and red regions. And the red region could be cancerous tissue, the blue region could be healthy tissue. We can then compare the biological molecular expressions of the different regions as visualized here in the mean mass spectrum of the red and the blue regions. And comparisons like these could help identify molecular differences in search of new treatments. And a final use case I want to mention is our ability to overlay high resolution microscopy images on top of these mass spectral images to enable multimodal analyses. And these multimodal analyses facilitate our clients' biomedical R&D and drug discovery. So these use cases illustrate that one of our main technical challenges is to deal with large data cubes, these so-called mass spectral images. Mainly, we want to interactively explore our data without needing to load the full data cube into memory. And we want to run distributed machine learning algorithms on our data sets to extract patterns and features used in downstream analyses. So in summary, like to be able to face these challenges, we need to efficiently process huge data arrays, which we could do by leveraging parallel and out-of-core frameworks. And so to efficiently process these huge data arrays, we're leveraging Dask, a popular and well-maintained framework that is supported by companies such as NVIDIA and Anaconda. If you're not familiar with Dask, you can compare it with Apache Spark, but with support for distributed data arrays built on the Python ecosystem. Like Spark, Dask has support for data frames, but more importantly for us, it also has support for distributed arrays, of which an example is visualized here. And as you can see in this figure, these distributed arrays could be backed by, for example, regular NumPy arrays. And this support for distributed arrays helps us distribute our data and manage our analyses. Additionally, our existing analyses pipelines are already built on the Python ecosystem and leverage the typical Python machine learning stack like scikit-learn, TensorFlow, and more recently also JAX. Because Dask is also built on the Python ecosystem, we can easily move our existing pipelines on top of Dask. So we can leverage Dask arrays as a wrapper around our data. We can use Dask to wrap the individual steps of our pipelines into delayed executions. And upon running our analysis pipelines, Dask will schedule these individual pipeline steps to be run on our cluster, while we can monitor everything with the integrated dashboard in Dask. For example, what is illustrated here is a typical computation graph of pipeline steps that are dynamically scheduled to be run by the Dask scheduler and executed on the Dask workers. So Dask can schedule and run our analyses pipelines. But how can Dask access the data? And for our use cases, we have a couple of desiderata. So first of all, while our compute platform at Aspect Analytics is built upon the Python stack, our user-facing application is built upon Clojure. And specifically, we would like to have a single shared data access layer that can be used both by Clojure and Python. And another one is like for different clients, we need to access different storage backends, which could also be mixed in a single deployment. For example, we might require access to files on Amazon S3, Microsoft Azure, or local network drives. And some of these object storage services charge by access. And ideally, we want to minimize the access to reduce both costs and reduce download time. Intelligent caching could also be a solution while speeding up data access. Dask itself provides solutions to some of these problems. For example, integration with object stores such as S3 can be done through an extension called FSPEC. However, we have been exploring Alluxio to tackle all of these problems at once, and we think Alluxio could be a good general solution to provide data access to Dask and more. Let's first explore why we're looking at Alluxio a bit more before we're going into details how we're combining Alluxio with Dask. So first of all, Alluxio is able to provide a language-agnostic file access through the Alluxio FUSE POSIX API. And this means we can access data from Python and Clojure without needing to write custom wrappers. I will go more into depth into this FUSE API in a few slides. Another advantage is that thanks to Alluxio's distributed and tiered caching layer, we can reduce object store data access and speed up downstream analyses by allowing data reuse over our distributed cluster. And by being a centralized data access layer, downstream clients don't have to deal with different storage implementations. What's more, we can completely avoid keeping object store credentials on client services. Other benefits related to Alluxio we have noticed are related to deploying it alongside our services. Not only is Alluxio easily deployable on cloud or on-prem via Docker and or Kubernetes, we can also deploy it for long-lived as well as short-lived deployments. What do we mean with long-lived and short-term deployments? To give you an example, we can have a long-running Alluxio server deployed alongside a persistent notebook server that's being continuously used by bioinformaticians to analyze data. However, we can also have ad hoc short-term deployments of Alluxio whenever we need to run a big analysis on a new data set. In this case, we deploy Alluxio momentarily, we can consume only the compute we need and use Alluxio as a data access and caching layer, similar how we use it on a long-running process, but only for the duration of these computations. And these short-term, short-lived deployments also give the option to integrate Alluxio into our automated testing systems without needing a dedicated Alluxio cluster for testing. So where exactly does Alluxio fit in as a data access layer for Dask? And how can Dask access our files and data via Alluxio? To illustrate this, let's say we have some data stored on S3 as is visualized here. And we have a cluster running two separate nodes, node A and B here, each running a Dask compute services as part of our Dask cluster that can execute one of our analysis pipelines. And this cluster is running a parallelized analysis, and each Dask service can run the analysis on part of the data set. For example, here, node A only needs access to data B and C, while node B only needs access to A and D. We can leverage Alluxio FUSE as part of an Alluxio deployment, visualized here, to make the required data available to Dask. When accessing the data, the local Alluxio workers will only load the data that is required by the local Dask process. And Alluxio will keep that data into local cache for further reuse. What is more, when the Dask worker nodes run the next computation and request different data on each local node, the Alluxio cache can redistribute the required data between the different nodes. So from these previous diagrams, you could see that our access point for Dask to Alluxio is the Alluxio FUSE client. And what exactly is this client and how are we using it? So let's first briefly explain what FUSE is. So FUSE stands for File System in User Space. Well, what does this actually mean? Well, the word file system is there because FUSE allows you to create a file system which allows you to access groups of data as folders and files, as a bit illustrated here. And this file system looks and works similar to the regular file systems like FAT and the extended file system you might have been using to access files stored on your regular machines. And similar to a regular file system, FUSE exposes virtual files through a POSIX-compatible file system API, as is also represented here in this file system tree. And so you can see that FUSE here is mounted alongside other file system mounts as this RAM disk and contains the data that we made available through Alluxio. So on the other side, we have the word user space. And this means that the FUSE client is run by the user outside of the operating system's kernel. Actually, like regular file systems run in the operating system's kernel, and usually to create a new file system, you have to modify the kernel of your operating system, something that you probably don't want to do. And FUSE, however, allows you to create a file system without needing to modify the operating system's kernel code. And the Alluxio folks have leveraged FUSE to expose your Alluxio unified namespace as virtual files that look and can be used just as regular files on your local machine, while in fact these virtual files are backed by the Alluxio worker cache and the mounted storage systems. So how do we connect Dask to Alluxio FUSE? As mentioned before, we use a Dockerized deployment. And using Docker, we can keep the services contained in their own environment. And so, for example, in this figure here, our Dask analytics processes are captured in their own containerized environment, as well as the Alluxio worker and the FUSE client, which run in their own Docker containers. And each host in our cluster is a Linux server that can run these services localized to the host. So besides the Dask service that is part of a bigger cluster, ideally each host also has their own Alluxio worker and FUSE client to have local data availability to the Dask worker. And so this local Alluxio worker will download the required data from the remote object store and make it available through the Alluxio FUSE client. We can actually leverage the host file system to share the data between the local Alluxio FUSE client and our local Dask service. By using Docker-supported bind mounts, we mount part of the host file system to both our Alluxio FUSE container and our Dask container, as is visualized here by these navy blue folders. And this provides a link between Alluxio and the Dask services. It actually allows Alluxio FUSE service to expose the Alluxio virtual file system to the Dask service via FUSE mount in this host file system. And this means it's possible to read and write data from Alluxio and to and from Dask without sharing other parts of the environment. So these processes are actually quite contained and cannot contaminate each other. The Dask processes can access just the data like they would from a normal file system without needing to know about Alluxio working in the background, because it all looks like regular files to them. And so by controlling the Alluxio FUSE mount settings and Unix privileges, we can carefully expose parts of the Alluxio namespace to dedicated services if needed. And this provides us a clean and secure way to use Alluxio as a data access layer for Dask. And so this is how we've been exploring Alluxio as a data access layer for Dask distributed machine learning. And to finish up with some anecdotal results, we build our own Docker containers instead of leveraging the existing Alluxio containers, mainly to reduce size and to have a bit more control. We found that deployments to be relatively fast, in the order of like 30 seconds to 1 minute to spin up the Alluxio services together with FUSE. And this is only a small slowdown compared to Dask pipelines that run for several minutes to several hours. Dask reading from S3 to FUSE was only 30% slower compared to the native Dask S3 integrations. However, we noticed that when reading large files that were already in the local Alluxio cache, we noticed a 10 times speed up compared to reading from S3 each time. And when we enabled the FUSE kernel caching, this gave an additional 3 times speed up when reading. So to conclude, from our experiments, we believe that Alluxio FUSE is a workable language agnostic data access layer that can be used together with Python, Dask, and other frameworks. In worst case scenarios, the data access layer has shown neglectable decrease in performance for our use cases. And in best case scenarios, we actually saw a significant speed up due to Alluxio's distributed caching layer. However, our work is not done. We're still exploring how to efficiently combine memory mapping of files together with the FUSE virtual files. And Alluxio also recently launched a beta version of a worker FUSE single client integration in their latest 2.5 edge release. We haven't been able to test this extensively. However, we've been told that this is supposed to speed up Alluxio FUSE data access even more. So thank you for listening, and I hope I might have given you some ideas on how to leverage Alluxio FUSE to integrate your data processing on top of Alluxio. Thanks.
Thanks, Peter, for presenting today. This is Adit from Alluxio. We have a few more questions, and just as a reminder to our listeners, feel free to ask questions on our Slack channel. And in case you have trouble joining the Slack, you can always post on GoToWebinar itself. Hi, Peter. So thanks for the interesting talk. I know you mentioned that you work as a machine learning engineer at your team. Do you mind describing what your team looks like in terms of people who manage the stack and those who are users of the thing that you presented today?
Yeah, so first of all, I want to emphasize this is some explorative work. So we're a quite early stage startup. We're still building out our product. The team currently is 5 people who are responsible of different parts of our system. And we're each building out separate parts of the system. The platform that we're building is supposed to first run predefined analysis workflows that we can get the data from, and these could be like machine learning models that actually make clinical predictions to generating reports on the data. To, as I alluded to earlier in the presentation, also connect to long-running persistent notebooks. So data scientists at our clients and internal could also analyze the data.
Makes sense. Thanks, Peter. In the way that you envision the end result, once it moves past the exploratory stage, how would you describe the end impact? I know you mentioned that it's going to be used for diagnosis, it's going to be used for certain drug discoveries. Do you mind elaborating on the end impact of a faster stack from a software perspective?
I'm not exactly sure what you mean, but I can give you a couple of pointers. So the technology that we're working is relatively new, and a lot of the current work is related to like diving into the data, like doing interactive visualizations, using these unsupervised machine learning methods to find patterns in the data, comment on them, analyze them, that then hopefully lead to new discoveries, to new treatments. We have been working with some experimental clinical diagnostic workflows where we actually have like a machine learning model that looks at some of these data. We have labels, we train these things, but this is all very novel and still for a lot of our clients very experimental because it's such a novel technique also.
Got it. Peter, we have a couple of questions coming in on Slack. One is someone is asking, are Alluxio FUSE and Worker 2 different processes?
So they currently in the 2.5, the stable version, and please correct me from the Alluxio side if I'm wrong, but there are currently 2 separate processes, and that's how we've been using them. So the FUSE is actually like a Alluxio client that can then connect to the Alluxio master and connect to the Alluxio worker to get data. However, in the Alluxio 2.5 latest edge release, I think it's like -2, there is actually an experimental integration of this FUSE client into the Alluxio worker. So this FUSE client can directly get the worker can directly get to the worker cache to then speed up data access. However, we run a couple of small experiments, but we haven't been able to test it extensively. We hope to test this more extensively in the near future.
Got it. Thanks, Peter. You nailed it. Like right now, as you mentioned, it is 2 different processes, but in the newer version, the beta version that you talked about, we are eliminating the RPC between the FUSE, which is a client, and worker, which is a separate process. Thanks, Peter. There's one more question on Slack. It says, you mentioned read speeds compared to S3 being 10x faster in terms of megabytes per second. Roughly what kind of speeds did that translate to? I assume it means what terms of Dask computation.
So and these are from the top of my mind, so like I might be a bit off there, but I think it was in the order of like half a second. We did some tests with like smallish, bigger files depending on your view, for around a bit smaller than 1 gigabyte. I think like 800 megabytes or something, and it took around half a second to load the file into Dask memory from the Alluxio cache. And I think if you enabled FUSE kernel caching, it was around 100 to 200 milliseconds or something. And I think that's also including the Dask part of it, if I remember correctly.
Mm-hmm. I think we have time for one more question, Peter, and there's one more on Slack, which reads, with Alluxio, given the data that FUSE just takes a portion of the S3 data, if so, how is data parceled out? Do you use filters, folder, or other means?
Not exactly sure what you mean, so maybe you can ask again if I don't answer your question.
Sorry, I was just reading. Yeah, go ahead.
Yeah, so how we deal with this at the moment is actually like we have our data on S3, and we typically pull like the one big image file, which can be multiple gigabytes in size, in one go from S3, and we then keep it into the Alluxio cache as one big file. And then I think as it works, I think Alluxio actually stores the file underneath in like blocks of like 64 megabytes, and I think these blocks can then be transferred between worker and client, but please correct me if I'm wrong there.
No, you got it, Peter. Thanks a lot, Peter, for your time. It was a very interesting talk. Thank you again for joining our conference today.
Thank you for listening and for the questions. Bye.
Take care.